About 4 minutes of other. I'm just going to start there so I don't repeat myself.
That's fine. Okay, it's recording. You're on.
Yeah, but again, Carver, thank you for joining us, and we look forward to everything that you got ahead of you as far as in your professional studies and findings that about our solar system. Something that I thought was really exciting as far as your outreach activities for science, and then turning right around and teaching. This was a new word for me, pedagogy. Am I pronouncing it?
Pedagogy.
Yeah, and that is awesome, teaching others as far as to teach. And then, of course, sharing your enthusiasm with the solar system. So thanks for that. And then your interest as far as understanding the stories that lead to the understanding the diversity of worlds around us in our solar system, and some highlights I wanted to give the group here, not to get into each one, but some of your research interests was awesome as far as formation of the Galilean satellites, Pluto and the Kuiper belt, Venus, atmospheric chemistry, Mars, South Pole, polar cap, what's going on there, lunar crater gravity, which I hope we'll hear a little more about as far as the years go on. And I was amazed, you've already released 20 publications or co-authored. But one thing I'm looking forward to maybe hearing or seeing more about is you make a reference as far as with Brian May, while you're waiting for data for a Rokoff that New Horizons was sending back and hopefully was receiving on this past New Year's. Looking forward to either a co-authored paper or maybe a new song, but sorry.
Yes, there's at least one paper that we're both co-authors on that came out after New Horizons flew by Erica. So.
Well, great. Well, again, your efforts tonight and ahead of us and in the past are out of this world. And on that note, I'd like to turn the mic over to you and welcome to our club. Thank you.
Yeah, thanks for having me. Let me try to get my presentation going and share my screen here. I do not have permission to share my screen.
Yeah, John's going to be helping us out with that.
Yeah, no worries. Okay. All right, let me try it. There we go. Looks like it's working. All right, so hopefully you guys can see that. So as was mentioned, I work on a lot of different worlds across the solar system, trying to answer lots of different types of questions. But a lot of my research has focused on Pluto, so I thought that's where I would focus tonight. And try to answer, this question of what is Pluto? What kind of world should we think about when we imagine Pluto and the processes happening there and on its neighboring worlds in the Kuiper belt? So what do I mean? What is Pluto? To kind of frame this question a little bit more, I thought I'd start with asking, what is the Earth? What do we mean when we think about the Earth? And one place to start is by looking at the surface. We have obviously a really complex atmosphere with lots of motions, a lot of chemistry. We have the surface, our surface ocean, all the continents and the diversity of geology and environments across the surface. But if we're thinking about the whole Earth, that's just the thin skin on the surface there. There's also so much more happening beneath with our mantle dynamics and core generating the Earth's magnetic field. And so all of these kind of inform that picture of what is the Earth. And I want to try to build a similar picture for Pluto tonight. So Pluto is way out on the far edge of the solar system, out in the Kuiper belt past Neptune, 40 times farther from the sun than the Earth is. And until the last few years, this was the best images we had of Pluto. this is the best you can do from the Earth. This is a series of Hubble images stitched together. And with these, you can see that there's different albedos on the surface. There's some different coloration. And that's about it. You can't really do any geology with images like this. And so, in 2006, we launched the New Horizons spacecraft. At the time of launch, New Horizons was the fastest spacecraft ever to be launched off the Earth, going more than 3 times faster than a bullet. And still, it took 9 years for New Horizons to make it from the Earth to Pluto. That's with the gravity assist at Jupiter a year after launch. And because it was going so fast, there was also no hope of slowing down and going into orbit around Pluto. There wasn't nearly enough fuel brought with for that. And so New Horizons took a series of images as it flew past in July of 2015. And the spacecraft continues to fly out through the Kuiper belts. We've had one more encounter with another Kuiper belt object, Arrokoth, which I'll talk a little bit about at the end. And we're in the process of searching for more objects that we might be able to visit with the spacecraft. When New Horizons arrived at Pluto, what we found was a more diverse and dynamic world than anyone had expected previously. The images we got back were just stunning and full of all of these different mysteries. We found tall mountains of water ice on the surface, smooth plains of nitrogen ice, and an atmosphere filled with hazes. So before I dive too much into Pluto, and I'll talk a little bit about its moon Charon here as well, I want to put it in another context, which is the context of the small worlds of our solar system, or the not planets, if you will. So here on the left, we have the Earth's moon to give you some reference for scale. There's the large moons of Jupiter at the top. Saturn has a much more diverse range of sizes in its moons. We have these kind of mid-sized satellites at Saturn and Uranus. And Pluto kind of sits at an interesting size range among these worlds. Because if I highlight the worlds that we're confident have subsurface oceans, well, it tends to be the big ones. And that's because these big worlds like Titan and Ganymede have a lot of heat being produced from radioactive decay in their large interiors. And because they're so large, they can have thick insulating ice sheets near the surface that keep that heat in. Europa and Enceladus also have subsurface oceans, but those are driven by tidal heating in both cases. Callisto almost certainly has a subsurface ocean, but our data is so poor there, we just don't actually have the data we want in order to confirm it. But it probably would be looped in to this group as well. So Pluto is just big enough that it might have been able to maintain a subsurface ocean over solar system history, but it's small enough that it might not have. And that was one of the questions as New Horizons went to explore Pluto, is what's under the surface. And the kind of the tools that we have for understanding Pluto, since we weren't able to stop and we only have this quick flyby, is for the very near surface, we can use spectra to get at the composition of ices. But really, when I'm saying that, I'm talking really near surface. That's really telling us about, say, the top centimeter of Pluto. Pluto is probably differentiated into in its interior with an ice shell on top and a silicate core beneath. And we can start to understand that ice shell and the history that it's had by looking at the geology at the surface. And in order to figure out kind of how thick that rocky core is, how much radioactive material might be mixed in relative to the amount of ice, we can look at the bulk density, which was another measurement made by New Horizons. So I'm going to kind of start at the top and work my way down throughout the course of this talk. And one of the most surprising things that New Horizons found was this atmosphere. We knew Pluto had an atmosphere before, but we thought it was much thinner. And no one expected the amount of haze that we saw in this atmosphere that's doing all this scattering, giving it a blue glow like the Earth's atmosphere. And it turns out this atmospheric haze is even cooling the atmosphere to much lower temperatures than had been predicted before New Horizons flew past the moon. And so because it keeps the atmosphere cool, the atmosphere isn't escaping to space as fast. It's trapping more of these interesting volatiles on the surface and allowing a lot more chemistry to happen in that atmosphere than we had thought previously. Going to the surface spectra, we found 4 distinct types of ices on the surface: methane, nitrogen, carbon monoxide, and water ice. 3 of the ices, so nitrogen, methane, and CO, are all concentrated in this large circular depression that's always front and center in these beautiful images of Pluto called Sputnik Planitia. This is a large basin, a large hole in the ground from an impact long ago. And because it's a low in the topography, the flows want to condense all of these cold ices into that basin to help fill it up. We also see some of these ices like methane and nitrogen kind of clumping towards the pole where temperatures are colder, as we'd expect. And water ice we tend to see only in places where it's not being covered up by these other more volatile ices that are moving across the surface. So we tend to see the water ice exposed at near the equator, where there's less methane ice coating it. Because as I said, this is really only telling us about the very thin coating on top. And when we start to look into the geology, we see all sorts of different varieties of terrains here. We can look at the edge of this big basin of Sputnik Planitia. And within the ice itself, we see this kind of cellular structure, all these little kind of blobby features here, which we think arise from the fact that the ice itself in Sputnik Planitia is convecting, that it's being heated from below just enough to slowly be overturning within this basin. This set of ice is probably something like 5 or maybe 10 kilometers deep at most. And it just takes a little bit of heat to get that nitrogen ice soft enough to start overturning. It's probably hard to see in this image, but there's also little dimples, little pits across these cells. And those are from the ice on the surface itself sublimating as it's exposed to sunlight. And so as it receives that sunlight, it starts to sublimate and these pits kind of grow with time. And so they tend to be really small towards the center of these pits. But as they get moved towards the edge where things are about to come back down, they grow and grow and grow. On the edge of Sputnik Planitia, we can see these mountains, big blocks of water ice that have maybe been broken off of mountain ranges. And we're still trying to piece together kind of the history of these blocks and how they were separated and what's happened there. If we go a bit south of Sputnik Planitia, we have these very strange features called Wright and Picard Mons. So it's this circular feature, and it looks like you have a little divot right in the middle there. And then you have flanks on the outer edge here, and then it tapers off. So looking at this at a glance, it has kind of the shape of a volcano. You have an inner caldera, you have your outer flanks and kind of smooth sides like a shield volcano would. And at first glance, this seems really exciting because you could maybe have water flowing up to form this feature. But we don't really understand how a water volcano or cryovolcano would work. Because you see, for molten rocks, if you melt rock, it's buoyant. in the Earth's crust. So you melt a little bit of rock that's less dense than the solid rock that it comes from, so it will want to buoyantly rise and erupt out at the surface. But that's not true with water. When you melt water, it's more dense. That's why the water ice floats. And so you need some sort of pressure to want to push that water ice up. It doesn't want to just naturally rise like liquid rock does. And so this is a feature that we really don't understand still. We see this kind of almost like hummocky texture, these ripples kind of on the side. And some sort of process built this big dome, something built up this mountain, and we don't know what it is. Even 5 years from the mission, this is still an area that we're actively working on. Kind of to the north, so a little bit higher latitudes, and a little bit off to the east of Sputnik, we have what's called bladed terrain. These are, because we're in a polar colder region, this is a region where during winter, we think that there's a lot of heavy methane ice deposited. And then we've gone into northern summer, which we're currently in at Pluto. This ice has been receding, been sublimating over time, and it leads to this really quite beautiful kind of rippley texture to the surface, what we've called the bladed terrain. As winds have kind of crossed over here, slowly removing material, not by erosion per se, but just by sublimating it off. So in the near surface, we have all of these different varieties of terrains. But what about the subsurface? That's where I want to focus kind of the second half of my talk here. So one of the most exciting discoveries from New Horizons, in my opinion, is several lines of evidence that at Pluto today, under that cold ice shell, surfaces are something like minus 400 degrees Fahrenheit. Under that cold ice shell is a liquid water ocean. And we have 3 independent lines of evidence that point us in this direction. Now I'm going to start with the line of evidence that I find most convincing, but is also the most confusing and hardest to understand. And this has to do with the position Sputnik Planitia itself on Pluto's surface. So I've kind of cartoon sketched in Pluto's spin pole here at the top. And Sputnik Planitia isn't on some random place on Pluto's surface. It's near the equator. And it's not just near the equator, it's near the equator and facing directly away from Pluto's large moon, Charon. Pluto and Charon are tidally locked. Both of them are, unlike the case for the Earth and the moon, where only the moon is tidally locked to the Earth, but the Earth is not tidally locked to the moon. In this case, both bodies are locked to each other. So one side of Pluto always faces the same side of Charon. Sputnik Planitia always faces away from Charon. So, okay, what is this telling us about Pluto's interior? Well, planetary bodies will reorient themselves on a time scale of millions of years in order to have the most stable spin state that they can. And in order to kind of explain this, I'm gonna pull out a Frisbee here. You see, there's a way that a Frisbee naturally wants to spin. And that's with most of the mass far away from the rotation axis. You can spin it the other way, but it's far less stable. And given enough time, objects want to reorient themselves such that that mass is far away from the rotation axis. We can actually see this with objects on the International Space Station. You take a bottle that has some sort of fluid in it that can dissipate energy, spin it, and it'll reorient itself to get more mass farther away from the spin axis, because this is a more favorable or a more stable spin state, and it takes less energy to rotate in this way. So what is this telling us about Pluto? Well, it's telling us that Sputnik Planitia is a mass excess, that there's more mass there. And so Pluto has reoriented itself to get that extra mass farther away from the spin axis. How could that be? This is a big hole in the ground. If you remove material, you have less mass there than you had before. Well, this can work if Pluto has a subsurface ocean, because that ocean will want to rebound underneath the basin and fill it in. Essentially, it'll look something like this. You have your basin, which is your hole in the ground, and the water ice will thin underneath to help support that basin. Because liquid water is more dense than water ice, it's a mass excess, pulling this region farther away. Now, as I started with, this is probably the most confusing line of evidence we have for the subsurface ocean. So I'm going to move in to the other two, and happy to talk about this more later during questions. But the other two are much easier to understand. The second is just that we see direct evidence for this ocean at the surface. We see fresh deposits of water ice and ammonia. And then ammonia is particularly important because ammonia, for one, degrades at Pluto's surface. So if you erupt some ammonia at the surface, over time, it's going to break down into other species as it's irradiated from both high energy solar particles and cosmic sources. And that ammonia is also a very effective antifreeze. So we would expect that as water from the subsurface ocean somehow made its way to the surface, it's going to be freezing along the way, concentrating any ammonia that it has in that until it can make it to the surface. We don't know how this material makes it to the surface, but it appears to be concentrated along cracks in the surface as well. And the last piece of evidence is by looking at these cracks themselves on the surface. Just like if you took a water bottle, stick it in your freezer overnight, come back the next morning, that thing is going to have expanded. You're going to have extensional cracks on the surface of that ice. Same thing happens on a planetary scale. If you have a global subsurface ocean and you start to freeze it, your whole surface needs to expand. You're going to be pulling the surface apart in extension. And the opposite is true if you're melting an ocean. If you're creating a subsurface ocean, you're going to be compressing your entire surface. So what do we see on Pluto's surface? We see lots of these big, long, extensional cracks where it looks like the ice shell is being pulled apart as the subsurface ocean is refreezing through time. So on Pluto today, it seems like there is an active subsurface ocean. And this raised a question for me and my collaborators, which was, okay, then when did Pluto get its ocean? Or is there any way that Pluto could have started off with its ocean? The kind of canonical view that people have had of how Pluto formed is it's forming in a very cold part of space. And so it probably formed out of very cold material. It probably formed as a mixture of rock and ice. And over time, that material is going to warm. This is some thermal modeling that I've done, where the y-axis here is kind of distance within the body. So down at the bottom here, we have the center. And here we have the surface where the ice shell is. And then we have time from the start of the solar system to the modern day on the right. And so we imagine that maybe there was enough energy as Pluto was coming together to separate out the rocky core from Pluto's ice shell. So everything in the bottom is Pluto's rocky core. Over time, radioactive materials are decay in the core, and that's going to cause it to warm up. So that heat's going to get into the ice shell, and that can melt that ice, cause an ocean to form. And then as you start to run out of heat from that radioactive material, that ocean's going to freeze through time. And when we run simulations like this, we find that we can have an ocean persist to the present day. There is some choice in your model parameters and how you want to simulate this. There's not just one answer you can get. You can get a lot of different answers. But with reasonable choices, we can match what seems to be the case in our observations. But we can make a different choice about how we start. We don't necessarily need to assume that Pluto started with a cold ice shell. And so we need some way of testing this, some way of comparing this model to the observations. Well, as this ocean is melting in the beginning, we should see compression. We're melting an ocean, we should be shrinking Pluto's radius, building compressive landforms, things like mountain ranges. And in the second half here, we should see extension. Now we're growing back out. But if we froze the entire ocean, we'd end up where we started. So we should have like net compression. So in the upper left, I'm showing the exact same plot I had before. And in the lower right, this is a plot of what I was saying, that initially we have some compression and then relative extension, but we never get back to where we started. And on the right-hand side, I'm showing another thermal history, another imagining of what could have happened if Pluto started with an ocean that initially froze very rapidly because it's being exposed to the cold of space. And then eventually that freezing starts to slow down because your ocean depth starts to equilibrate with the amount of heat being produced by radioactive elements. And then we get a second, more prolonged period of freezing, very similar to kind of the end of our cold start simulation. So here we would expect a period of early extension, and then it would kind of slow down for a while, and then a second period of much slower extension as you're running out of heat-producing elements. So what do we see when we look at the geology? Well, as I mentioned earlier, we see certainly widespread evidence of recent extension. This is certainly supportive of that hot start case. And you could argue that it could work for the cold start case too, if you somehow erased the surface, if you don't preserve your terrains from those earliest moments in time. The thing is that on Pluto, we see areas that are heavily cratered, kind of like in the lower right side of this image, that we think are roughly the age of the solar system. Most of the craters we see on planetary bodies were produced very early in solar system history, because that's when you had lots of leftover debris to do that cratering. And even on those oldest terrains on Pluto, we don't see any clear evidence of global compression. So do we see any evidence of early rapid extension? And the answer is maybe. This is a topographic map of Pluto. We have that big central depression of Sputnik Planitia. On the left, we have those 4 extensional fractures that I've been pointing out before. And when we look at Pluto in this view, something else comes out. There's this big, what appears to be global feature that we call the ridge trough system. This appears to be a giant tectonic structure. It appears to be older than this giant basin of Sputnik Planitia itself because it's not deflected around it at all. It looks like Sputnik Planitia came right in on top of it. And because this feature is so old, it's really degraded, which makes it hard to interpret. And there's still active work in trying to understand its formation. But probably the most clear aspects of it are this deep trough on the western side here that looks to be extensional. Things kind of in the center of the ridge trough system seem to be a little bit of a jumbled mess for reasons that we're still trying to pull apart. So this appears to be an ancient feature that is at least in some sense extensional and maybe has other processes going on and doesn't have clear evidence of compression. So kind of tallying things up, we think that in general, the evidence we have at Pluto favors this hot start, favors this idea that Pluto might have started with an ocean. But how? It's forming in a ridiculously cold part of the solar system. How would it form with this ocean? And there's two ways that could happen. One is it incorporated aluminum-26. Aluminum-26 is this element that existed for the first few million years of solar system history. And asteroids and other inner solar system objects that formed with aluminum-26 all melted. And I'm talking silicate rock melted, because this stuff releases a lot of energy very quickly. But because it releases a lot of energy very quickly, it decays very fast. It has a half-life of less than 1 million years. So worlds that formed in the solar system after the first, say, 3 to 5 million years of solar system history did not form with any aluminum-26. So did Pluto form early enough to form with aluminum-26? From other work that I've done, other authors, we think that Kuiper belt objects actually formed pretty late into solar system history, probably after 5 million years. So we don't think it's this highly energetic source of radioactive material, which means the only other heat source we really have as you're putting together Pluto is the heat of accretion itself, the heat of impacts coming in on the surface. And the way to think of this is that when you have impacts building up a body like Pluto, each impact on the surface is like an explosion. It's releasing a lot of energy very quickly. This is why almost all craters in the solar system are circular and not elliptical as they come in at various angles. And because you have this giant explosion, you're heating up the ground underneath you. Now, if you have a lot of time in between impacts, you can just radiate that heat to space. You have enough time to cool off. But if you're forming quickly, then you have impact after impact after impact all on top of each other. You keep warming the surface repeatedly. And then you can get temperatures warm enough to start melting your water ice, to start forming an early ocean. And we find that Pluto would have had to form faster than about 30,000 years in order to have had this early ocean. And that seems incredibly fast. It took the Earth of order millions of years to form. Now, Pluto's a lot smaller than the Earth. It was forming in a very different part of the solar system at a different time. So there's no reason to think that they should be the same in the processes that were going on. But still, faster than 30,000 years. Well, the nice thing is that other authors trying to understand other aspects of these outer solar system worlds, like the fact that many of Pluto's neighbors in the Kuiper belt all seem to have moons. Moons are rare in the asteroid belt and common in the Kuiper belt. And one of the ideas is that maybe if these worlds were forming very quickly, forming at the same time, they're forming very close together, so a lot of them would form in binary systems like this. So we seem to have multiple lines of evidence all pointing towards the fact that in the outer solar system, worlds formed fast. So what does this mean? I'm going to come back to that. It means that oceans may have been common in the outer solar system. These are the best images we have of the other two of the other large Kuiper belt objects. Eris is about the same size as Pluto. Makemake is a little more than half the size of Pluto, kind of similar to Pluto's moon Charon. And for both these worlds, we have no resolved images. But if they also formed quickly like Pluto, we would expect they would have also formed oceans. Would those oceans have survived to the present day? We don't know. That depends on how many radioactive materials they formed with, how their ice shells that insulate those oceans evolved with time. At Pluto, it seems like it kept its ocean. Maybe these have very similar stories or very different ones. And we won't know until we go visit them and see what the geology on their surfaces looks like. And to kind of bring things back, I also want to just again highlight how rich a world we've found at Pluto. This world with an ocean that seems to have topography on its base, supporting large basins that are filled with exotic ices that themselves are convecting and moving around, creating these cells at the surface. We have geology that seems to span the entire age of the solar system, from the most ancient times in its formation to active processes going on now, interactions with its atmosphere. And I'll end things there. Thank you very much for giving me your time. Happy to take questions.
Well, Carver, I've got one, but before
Yes.
I ask, again, thanks, and this is awesome. And as we go through this, if there's anything we can do for you, please let us know. Letters or. But the question is, when talking about the extension, you earlier talked about the rotation as far as Pluto and Charon, how that might affect the extension. Is there any prediction on the rotation in the past when these extensions occurred to now, or any evidence? You kind of know what I'm getting at. I'm using the space station example you were showing with the bottled water rotating.
Yeah, so one of the hard things about these sorts of systems is that essentially, I'll go back to this video.
Oh, okay.
When it's rotating, once it gets to that end state of its kind of locked in place, you've kind of lost all the information about what happened before that. It's in its ideal spot that it's made it to. It's in its lowest energy state. And so there's no way of rewinding the clock on that. Same with Pluto and Charon in their orbits today. They're both tidally locked to one another. And so we know that at some point they despun, they locked into that place with each other, but we can't say when that happened. It just implies that some process got it there at some point.
Okay.
Now, one thing I can say is that because this implies, you're trying to get that mass away from the rotation axis, if Pluto's subsurface ocean were to entirely freeze out, then this is, once again, just a big hole in the ground. It's mass low. And so it would want to wander back towards Pluto's pole, back towards the rotation axis. And that happens relatively fast on geologic timescales. And so we think that the fact that it's here implies that the ocean is still here today, and not that it just was there in the past.
Okay. Awesome.
Robert raised his hand.
Yes. Thank you, Carver, for a great talk. I had a comment and a question. The comment, I was really impressed and interested in kind of a human element that Clyde Tombaugh, as a young man, of course, at Lowell Observatory, discovered Pluto, and then some of his ashes, I understand, were actually on board the New Horizons as it passed the very planet that he had discovered. And I don't know how many people knew that, but my question is about the there's a layered atmosphere, kind of a laminated layers. Do you know much about how did it occur, or how does it persist?
Yeah, so let me bring up that image. Yeah, those layers are really lovely. I'm not sure how clearly it comes through over Zoom here, but these layers would have to be actively maintained because they aren't all that thick, maybe a few kilometers thick, and it's an atmosphere, it's a fluid, it's always moving around, you have lots of oceans. So our idea for how these are maintained is it's probably waves that propagate upwards through the atmosphere. that carry energy with them. And they're also going to concentrate these hazes that we see into these discrete layers, maybe by having small temperature perturbations or by kind of dynamically focusing these different aggregates, these materials there. And again, I'll say kind of like with everything with Pluto, this is something that may change as we start to understand it better, because we're still taking these images and trying to figure out how big are the particles in this haze? How many different kind of sizes are there? What's the chemistry that's making them? And once we understand that better, the exact process that's maintaining the hazes might become more clear to us. So we think it has something to do with waves moving in the atmosphere, and the details we're still trying to figure out.
Cool.
Okay, Chris raised his hand.
Thank you, John, for recognizing me, and thank you, Carver, for giving us these insights. It's a real treat to get these insights on the geology of Pluto. And I noticed that the Pluto-Charon system is similar to our own, and how the moon is tidally locked to the Earth, and how there may have been, or is theorized to have been, quite a bit of influence of the Earth on the near side of the moon, and how come there's so much looks like volcanic lava and so forth spilling, the Maria. Is there any evidence of that happening in the Charon Pluto system?
That is a question I would love to be able to answer, but we really can't because we don't have the data. New Horizons flew by in basically a day. And so we have these images and we can see very clearly the geology for one half of Pluto and one half of Charon. And I don't know what the geology on the other half of these worlds looks like, at least not at all to the same resolution. We've been using some of the images we got as it was farther out to try and piece that together. And we don't see any obvious differences between, say, the near side of Charon, the side that's facing Pluto, side away from Pluto. But if there was subtle differences, we probably wouldn't see them. I don't think there's anything as dramatic we have on the moon, where you have the Mare on the near side and the highlands on the far side. That kind of big difference we should be able to see. So nothing that dramatic. More subtle things, maybe. There's a big circular feature, it looks like, on the back side of Charon. Is it a big impact basin? Is it something else we just don't know? Because the images aren't good enough. We'd have to go back with an orbiter to find out.
Wow.
Okay.
Thank you for that.
Two questions. How true are the colors we're seeing in this image? And were you going to say something more about the data from Eris, the Eris encounter?
Oh, yes. Okay, so these colors are stretched quite a bit so that you can see the difference in the trains. This image, which I was showing a lot of, is probably the closest to true color for Pluto that we can get with the filters that we brought with on the spacecraft. To human eye, it'd probably look pretty brown in most of these places. And that makes sense. A lot of what's giving its coloration is methane, right? It's this kind of organic sludge on the surface that's been processed by a lot of solar radiation. Yeah, so a year ago, January, we flew past Arikoth, which is this other really strange world. And because we flew by it just a year ago, we're still very much in the process of understanding what's going on. This is the best image that we got. Because it's such a small world, we got a lot less data than even for Pluto. What we can say is that probably the strangest thing about this world is that it appears to be shaped like two pancakes kind of stuck together. I have a little 3D printed model of it here. So the view you're seeing is kind of face on like this, but it's actually very thin in the other direction. And we got just enough images to confirm that it does have this really thin shape. Now, how you make two pancakes in space and stick them together as you're forming them out of what probably is very weak material, so you probably have to do everything very gently to prevent them from just squishing together. We don't know. So this body is very much an active field of research right now and trying to understand, what are these pits on the surface? Are they impact craters or something else? There seems to be some sort of big circle in the center. What's going on there? There's a lot more mysteries than answers right now in understanding this world.
Andy was going to ask a question, I believe.
Yeah, I've actually got a few. First off, what are the relative ages of the recent cracks and that ancient fault feature?
Yeah, ages on Pluto are hard to get. So what we can say is this fault feature is probably very, very old. It's probably from the earliest stages of the solar system, just because it's older than this big impact basin. And very large impactors that could have made something like this probably weren't around past the first few, say, 100 million years of solar system history. But all we have when we're talking about impacts like this are these kind of probabilistic arguments. So maybe one happened to stick around later. We just have no way of knowing. And these other cracks that we see on the left here are definitely younger, because in the detailed images, we can see them interacting with craters. They seem to cut straight across a bunch of craters, and we see almost no craters on top of them. So they appear to be very young. Ridge trough system seems very old. Absolute ages, we really don't know for Pluto.
And then I just wanted to follow up on this whole idea of elliptical craters versus circular craters. I know at Meteor Crater in Arizona, they were looking for the impactor in the center of the crater. Logic would dictate that's where it would be, and it ended up being, far off to one side. But that's still a fairly circular crater.
Mm-hmm. Yeah, so impacts are a really interesting thing, because you have a fairly small object coming in. A general rule of thumb is that the crater that you produce is something like 10 times bigger than the impactor that made it. So Meteor Crater, if I'm remembering right, is something like a mile in diameter. And so whatever produced it is going to be about 1/10 of a mile in diameter, much smaller, a few hundred feet across, 500 feet across or something. And so what's making the crater is not this object burying into the ground. What's making this hole in the ground is the object hitting the surface and releasing all of its kinetic energy. And when it does that, the material that it's hitting just moves out of the way all of a sudden. So it really is like an explosion just excavating material. And because of that, it doesn't really matter what angle the impactor came in at, it's still going to release that kinetic energy into the surface. The only exception is if you came in at a really shallow angle, and then you can kind of skip across the surface or drag that energy a little bit farther along as you make your crater. But if you look at, craters on the moon, they're basically all circular, but we don't expect that all those impactors are coming in from 90 degrees. And we see very few elliptical craters, just because you have to be at such an extremely shallow angle to make those.
Cool. And then last question, I'm kind of on the edge of my seat to find out if what are the prospects of finding another object for New Horizons to visit in the years ahead?
Yes. What I can say is that we are very actively looking. We're using telescopes from around the world and space telescopes in order to search. And, we don't know exactly what the process is going to be. Last time when we were looking for Arakoth, we found 2 potential objects. Arakoth, another one that I'm not going to remember the name of because it was never given a clean name to use. It just has some catalog name somewhere. I will say that our telescope time, unfortunately, has been impacted by COVID, like everything else in the world. So, and we've also been hit by poor weather on some of our observing nights. And that's the way things go. But we're going to keep searching. Spacecraft is healthy right now. We still have we have half the fuel that we had when we were leaving Pluto, essentially. We used basically half of it to do the Arrokoth encounter. So we think we have enough to do another one if we can find an object. And we're looking. We just don't know.
Great, thank you.
Anyone else have any questions for Carver?
Yeah, hi, I have a question. I was sort of curious about the ocean you mentioned and that it was water. Do we know that it's mostly water or a variety of different liquids, or what do we know about that substance?
We expect that it's almost pure water. And essentially, in some sense, this comes down to what materials do you have to make large worlds out of when you're building them in early solar system history. You know, solar system is abundant in the simple elements, things like carbon, oxygen, hydrogen. And so water is simple. You just need some water, you just need some hydrogens and oxygens. So you had lots of water available, and it was all condensing in this cold outer part of the solar system as you're building these worlds. And there's just not that many other liquids that are going to be around in any abundance. Now, what might be mixed in here is lots of things that help keep that ocean liquid. So lots of things to help it have antifreeze. Things like salts, things like ammonia might be concentrated in there, which again is a pretty simple molecule. It's just some nitrogen and hydrogen. So there's probably some chemistry kind of along those lines, or other salts or dissolved materials that have kind of leached out of the core into the ocean over time. So we think in bulk it's water, probably impurities in there, and maybe some antifreeze to help keep it around.
So, excuse me, Carver, this is Gary. Are you saying then that you think that the water formed, as water from the hydrogen and the oxygen way out there? So no additional special amount of energy, it just formed. You didn't need any special process to do that?
So what I'm saying is that as the solar system was forming in general, right, you have a disk of material around the sun. And in the inner part of that disk where the Earth is warming, things are very warm. So you're just going to have water gas. And the things that condense out of that disk are going to be silicates, are going to be the rocks that went on to form the Earth. In the outer solar system, where you're forming Pluto and the ice giants, it's cold enough in that disk that water can just condense out. So in the disk itself, there would be chemistry that drives that hydrogen and oxygen to form the water. And then once it does that in the disk, it's going to condense, form ice, and that's going to go into being accreted and forming Pluto.
Okay.
So anybody else have a question?
Yeah, I have another question. The Sputnik Planea, do we know what object hit it? Was it Charon, or do we know much about Charon as well? Its features in relation to Pluto?
Yeah, Sharon. So, all right. To your first question, we don't know the object that hit Pluto to form Sputnik Planitia, because it's probably was totally destroyed in that impact and has probably been mixed into Pluto itself. There's probably no remnant of that left. Planetary collisions tend to be violent affairs. Charon itself, the current thinking is that it actually probably formed from Pluto in an impact, kind of like the Earth-Moon system, where you might have had two similar sized worlds impact each other. Most of the material goes into Pluto, and a lot of material gets flung off to form Charon. And there's some little debris that would be left over to form the other small moons of Pluto, which I left out of this talk, which are Hydra, Nix, and Styx. And those are all very small compared to these. On this scale, you wouldn't even be able to see them. They're really tiny worlds. To Charon's geology, it's not as diverse as Pluto because it's about half the size of Pluto, which means you have a lot less gravity. And so just gravitationally, you can't hang on to an atmosphere, which means you're not going to have as interesting a mixture of ices. Charon's surface is almost entirely pure water ice. There's a lot of cracking on the surface, lots of big canyon-esque features that might hint at a very early period in Charon's history where there was more going on, where maybe it also had an ocean very briefly that froze out. But again, we don't really understand this history very well. It seems like things definitely moved around and something happened early on, but we don't know what.
Okay. Awesome.
Okay, I'm going to go ahead and end the recording, but we certainly can
Okay.
continue to chat.